My
He's
first
at
student.
Stanford, right?
Oh,
Oh, okay.
oh,
Just
sorry.
no,
Yeah,
just
he was one of
telling
my
me
first
that.
students here at Bergen, so it was interesting to see what he's up to and meeting a person such as yourself. So I'll mute myself. I have my students writing down questions they might have for you, either before or during your presentation. I'm sure afterwards we have some time that you can answer maybe some questions for them. But I'll try not to interrupt and just let you give your presentation, and we'll talk at the end.
Hi, my name is Dr. Reva Kay Williams, and I am an astrophysicist. Today, we are going to talk about extracting energy from rotating black holes using the Penrose mechanism. Now, I like to start my talk off by giving honor where honor is due, credit where credit is due. Some of you all may notice these scientists. They are Sir Isaac Newton and Albert Einstein. Not only did these scientists, with their laws and theories of gravity and motion, lead us to the knowledge of black holes, particularly Einstein, but on a more personal level, these scientists are the reason I'm here today giving this talk. That is early on in my quest to find out which area of science I wanted to pursue as a career. When I was first introduced to these scientists' laws and theories of gravity and motion, I fell in love with the physics. And that basically sealed my faith in my becoming an astrophysicist, one that studies the physics of the universe. So my agenda today, first I would say something briefly about my childhood, my high school, and my college years pertaining to my studying astrophysics. Then I would talk about motivation and a general background. And then I would give you an overview of what black holes are and how they form. And then I would talk about non-rotating black holes and then rotating black holes. And in that part of the talk, I would talk about the Penrose mechanism. Then I will conclude and finally take questions. So let's get started. Now, my earliest childhood memory concerning the sky is that one day, and I was about 4 or 5, well, actually about 4 or 5 years old. And we were playing out and it was late at night. And I think my parents probably were talking or something with the neighbors. So we were rolling down this hill, as kids do. And somehow I focused on the sky and it was a lot of stars. So I must have been looking down the Milky Way. And I was wondering what they were. And then the thought came to my mind about it was a old superstition about if you pointed at a star, that you would get a bump on your eye and they called it a star. So I knew not to point at stars. So, but from that point on, I just loved stars and I would get braces with stars on it and clothes with stars on it. So that was my first introduction to stars. And as I was growing, I think I was about 6 years old, and my grandmother, she would get this thick catalog from Sears, and that was before online shopping. And I would just turn to the chemistry sets, and I just love looking at them, and it just sparked something inside of me. And I never got a chemistry set because I never asked for one. And also, I always loved math. In my high school days, I remember studying Isaac Newton's laws, and I liked them, but then I wasn't, I didn't know how important they were. And I liked algebra and geometry. And another one of my classes was having fun. Okay. Um, and then, so that was high school. In college, so before I went back to school, after high school, I worked at an insurance company. And first I started out, I was like a mail clerk. And then I had advanced to a claims adjuster. But I didn't want to be there that long. And it was people there saying they had been there like 25 years or something like that. And I didn't want to be there that long. So I started having challenges in life, as we always do. And now I know it was just to make me stronger. But after the challenges, and I'm religious, so I prayed to God and just asked him to help me. And so about 2 weeks later, I was like, I was in the washroom, And all of a sudden, a voice came to me, and it was like, it was in my thoughts, but it was really powerful. And he just told me, like, to look at my life and stuff. And he said, go, I want you to go back to school. And so it was clear, and it wasn't my voice. And so after that, that was like in the February of that year, and that I quit my job and I prepared to go to college. And so I enrolled in Malcolm X Junior College that following fall. So when I got in there, I wanted to be a scientist, and so I didn't know which field I wanted to pursue as a career. So I would read books on how to become a scientist, and this was during my first semester there. So in the book, they would give examples of the different scientific fields. And so when I came to cosmology, which is the study of the universe as a whole, I knew that that was my calling. And so I said, like, well, I believe that God created the universe, and I wanted to find out how he did it scientifically so that I could tell people. So that began my journey in college. While there as an undergraduate at Malcolm X, I fell in love with Isaac Newton's laws and Einstein's theories and laws of gravity and motion. At the time, I didn't realize that they were two of the greatest scientists. But I fell in love with their laws because they seem to relate to our lives, and so they are the laws of motion. And it made me like really think about how people move in life, and so that was like that was my love, and I wanted to find out more about them. And also, I didn't realize at the time that they both worked on gravity. So now we come to the part motivation and general background. Now, my motivation was quasars. Quasars were discovered in 1963. I'll talk more about them later. But quasars are the most distant objects in the universe. At least they were at the time. I think they're like the second most distant now. And they are associated with jets. Some of them have jets and some do not have jets. The ones with jets, they call them radio strong quasars. And the ones without jets, they're radio quiet. So when I say radio, I'm saying that their emission they emit radiation in the radio regime of the electromagnetic spectrum. And then we believe that from observations that the radio strong quasars evolved to radio galaxies, and the radio quiet to evolve to Seyfert galaxies. And as a group, these are called active galactic nuclei, or AGN. So the historical ways to extract energy from the black hole was from accretion disks. That's one of them, in which binding energy, gravitational binding energy is released as objects fall in toward the black hole. Then you have radiation being released from orbital differential viscous or like friction in an accretion disk. And I'll talk more about the accretion disk later. And then magnetic stresses also produce radiation. And then there's the Penrose mechanism, which uses rotation of the black hole. Now, briefly, the Penrose mechanism, it was proposed by Roger Penrose in 1969, and it allows rotational energy to be extracted from the ergosphere of a rotating black hole using the Kerr black hole metric. And so I'll explain that further later. Now, the AGN, the models proposed were, there were many accretion disk models proposed, and there was very little rotational energy extraction models, which would require general relativity. Well, I know how your mouth gets dry. So relativists, people that study general relativity, or relativistic astrophysicists, they were saying, well, what about the black hole? Like, where are the effects of general relativity? And so the relativists, they were disappointed. then they were saying, well, we have this 10 to the 8th, okay, that's 100 million times the sun's mass, supermassive black hole. Yet it appears that it has no significant role in producing the spectra of AGN. And remember, AGN, it's quasars are fall into that category. So I took on the task of finding out the effects that the black hole has on the spectra observations of AGN. And when I say spectra, that's saying that referring to the electromagnetic spectra, and we can only observe objects or study objects by the light that we get from them. So when I say spectra, we're really talking about the light, the energy that's along the electromagnetic spectrum. So when I got in graduate school, I basically had my mind made up that I wanted to do something significantly or contribute significantly to our understanding. So I looked at it and I found out where, objects that were mysteries to us. And so quasars were. So after I got in graduate school, and I wanted to create a model that would explain the energy source of quasars and also explain how the jets are being emitted. So my goal was to create a model to explain the core energy source of quasars and other active galactic nuclei, and to create a consistent model to explain the generation of the polar jets emitted from the cores. And so this is a picture, this is an artist's conception of a quasar. And this part is the accretion disk. So matter falls in along the accretion disk and toward the event horizon, and then something takes place, and I'll tell you what takes place later. And these jets are emitted at the polar regions. So this is an artist's conception. I think it's an artist's conception. It actually looked like a real photograph of a quasar. And then this is a active galactic nuclei. This is the Seyfert galaxy. So let me say something about Isaac Newton's laws briefly. Sorry, I'm gonna make sure I get my time. Sorry about that. So the Isaac Newton's laws of motion. The first law is the law of inertia. So it says that once an object is in rest or in motion, it would continue at rest or in motion in a straight line at a constant velocity unless acted upon by some outside force. The second law is that force is equal to mass times acceleration. And I would say that our mass, it doesn't change. So this would be our mass and our acceleration. The force we have is the way that we accelerate in life. Now, this is what I came up with when I was an undergraduate. And then the third law, it says for every action, there's an equal and opposite reaction. So that law is biblical. That's like what goes around comes around, you reap what you sow. So I just thought that was fascinating. And so I want to say something about the universal law of gravity. Now, with Newton's laws of gravity, universal law of gravity, he looked at gravity like the mutual force between two masses at a distance. And so the closer they are, the greater the force they're going to have. And so that's almost like, together we stand, divided we fall. Okay, so now this brings us to an overview of what black holes are. Black holes were predicted to exist from Albert Einstein's general theory of relativity in 1915. His theory described motion in a gravitational field. It describes where it shows that clocks run slower in a gravitational field. And then it shows that space-time is curved around a massive object. Now, this is the way Einstein defines gravity. This is a rubber sheet analogy. And so this is space-time. So, this is space-time. And so if you have a large mass and you put it on this space-time continuum, which can bend and warp, then it takes and bends it and warps it around the massive object. And so the less massive object, the less warping you have, or the bending of space-time. And here is a small object. And so what Einstein said is that what gravity is that when space-time is bent toward this object, then objects that come in, if they have angular momentum, then they're going to circle around and they will be trapped. And the angular momentum will keep them from falling in toward the, say the black hole. This is my drawing. And so this is the mass, and this is space-time. And so these would be trapped orbits, like our planet. Now, the difference between Einstein and Isaac Newton's laws of motion is that Isaac Newton's laws of motion govern small gravitational field strengths and also slow velocities. Einstein's theory and laws govern objects that are moving close to the speed of light, or particles that are moving close to the speed of light. And also, it governs large gravitational fields. So black holes are one of the most fascinating objects in our universe. They are a storehouse of a tremendous amount of energy. It was not until the 1990s that we began to understand the physics of black holes. My work of 1991, my dissertation, and then my publication of my dissertation in a paper contributed significantly to our understanding of black holes, the astrophysics of black holes. For example, my work allowed us to extract energy from a black hole. It allowed 3- and 4-dimensional numerical simulations, and that acronym means General Relativistic Magnetohydrodynamic numerical simulations. So it enabled us to be able to have matter accreted onto the black hole in 3 and 4 dimensions. And that means like 3 space components and a time dimension. And when you're talking about momentum, it's the 3 momentum components and the energy divided by 6, the speed of light. So it allows us to do those calculations and use orbits that are near the horizon or the event horizon. And that's inside the ergosphere, and I explain that more. In 1994, the Hubble telescope confirmed that supermassive black holes indeed existed in nature, because when I first started working on them, they were just theory. They hadn't been confirmed that they actually exist in nature. Black hole masses can range from greater than three times our sun's mass found in the galaxy to the size of a galaxy. And that's of the order of 1 billion times our sun's mass. So they range, it's a large range of masses, but the physics are the same for the stellar-sized black holes and the galactic-sized black holes, or the supermassive black holes. So in addition to gravitational stored energy, black holes can have rotational energy as well as electromagnetic energy. And there's a theory that states that we can only know about the mass, excuse me, maybe I should just put this one down. Okay, we only we can know about a black hole is its mass, its angular momentum, and its charge. So, for example, with supermassive black holes, we don't know if it started off as being a supermassive star that evolved into a black hole, or was it a cluster of stars that evolved into black holes and merged together to make a supermassive black hole. So we don't know that. So we don't know what a black hole was. The only thing we know is its mass, its angular momentum, and its charge. And the angular momentum is how it's rotating. So black holes are believed to house the most internet objects in our universe, such as the mysterious quasars and gamma ray bursts. Now, quasars, as I said, were discovered in 1963, and they are the most distant objects in the universe. What's mysterious about them is that their energy output is 1,000 times that of our galaxy, yet they're no bigger than our solar system. So that's a mystery. They are associated with polar jets. That's jets that are along the z-axis, is one way to say it. And they are associated with very energetic particles, electrons, and which come in the pairs sometimes. And so electron-positron pairs, that's a negative electron charge and a positive electron charge. They're associated with photons, high energetic photons, and perhaps protons, but most likely not, because protons are so heavy and it's hard to get them up into a jet. And we know that they're associated with magnetic fields because of the synchrotron radiation. So here we just go through some pictures of quasars or AGN. Okay, now this is a quasar. This is actually a real photograph of a quasar. This is actually a real photograph also. And this is the AGN, active galactic nuclei. Here this is the core where the black hole exists. And then you have the jets extending outward to very large distances. So this is a quasar, or active galactic nuclei. And here you see the jet, and then the counter jet you can't see, and that's because of Doppler boosting, because this jet is pointed towards us, and so it's Doppler boosted to higher energies, and so we can see it, and this one is pointed away, and that's it's basically found in it's boosted away from us through Doppler boosting, and it's probably boosted to lower energies and maybe the infrared or something, so we can't see it in the visible. And this is an artist's conception of a Seyfert galaxy. And here it looks like, they tried to create a jet. But some of them are associated with jets and some are not. Now, this is a photo that was taken by the Hubble telescope when they discovered that most galaxies have supermassive black holes at their center. And this is a picture. This is a spiral-shaped galaxy like our Milky Way. And here at the center, they're glowing. That's where the black hole is. And then you have the galaxy in the spiral arms. Now, this is a picture of an elliptical galaxy. The elliptical galaxies are usually associated with the most powerful jets. So here you can't see the jet, and that's probably because the jet is in the radio, and we can't. This is a physical picture of one in the visible of the electromagnetic spectrum. So gamma ray bursts, give my word again. Gamma ray bursts, they were discovered in the 1970s, and they appear to be the most energetic event in the universe. So the gamma ray bursts, they can last from milliseconds up to minutes. Now, we know, or we believe, and about now we kind of know it, that gamma ray bursts are associated with the birth of a black hole. And the way black holes are born, it could be from a supernova explosion prior to the formation of a star. And I'll say something about formation of stars later. It could be formed by two neutron stars colliding to form a black hole, because the mass of the neutron star would be enough to form a black hole. And then it could be a neutron star being swallowed by a black hole. Now, formation of black holes. Okay, black holes are formed from dying stars gravitationally collapsing after they have exhausted their available energy that allowed them to shine. And that's because what allows them to shine is that their thermonuclear reactions are taking place at the core. And those nuclear reactions, they balance the star such that it won't collapse under gravity. So there are three ways in which a star can die. It depends on its mass. If the mass is about 3 times our sun's mass, or like our sun. Then a white dwarf will form. And how a white dwarf forms is that once it has depleted its available energy at its core to shine, then gravitational forces start to collapse. And it will collapse under gravity until the electrons around the nucleus, they put up a pressure and they halt the collapse. And then we have a white dwarf forming, and the star then is about the size of the Earth. And a teaspoon of that star, since it retains its mass and its gravitational field, a teaspoon would weigh about 2 tons. And also they're made after they form of crystalline carbon, and crystalline carbon is a diamond substance. So we have diamonds in the sky as big as the Earth. The next way a star can, the star dies is that it forms a neutron star if the mass is greater than 3 times our sun's mass. And a neutron star is called a neutron star because after it exhausts its available energy to shine, then it starts to collapse. The electrons around the atoms are not able to halt the collapse. So the electrons are squeezed inside the nucleus and form neutrons with the protons. And you have a neutron star, and the neutron star collapsed to about the size of a city, a big city. And what's spectacular about it is that it rotates on its axis about every 1/10 of a second. It has a very large magnetic field, about 1 trillion times the magnetic field of our sun. And if the magnetic axis is inclined to the rotational axis, then it's called a pulsar, because when it sweeps past the observer's line of sight, it gives out a pulse, so pulsar. So the third way that happens when a star dies, if this mass is greater than 10 times our sun's mass, then nothing can halt the collapse. So in this case, gravity dominates. And when gravity dominates, the dying star continues to collapse. It will continue to collapse, and it maintains that mass that it has. Well, it ejects some of the mass as it's collapsing and to form new supernova explosions. But most of the mass is retained. And as it collapses, the gravitational field becomes stronger and stronger until no light cannot escape. And when that happens, then it's a black hole. So this is just a diagram that I was to represent the light rays. So when the lights are emitted, when light is emitted, then the gravitational field pulls the light back down. And so all we observe is like a shadow or a black hole in the universe. So I want to say something briefly about non-rotating black holes. The physics of non-rotating black holes was worked out by Carl Schwarzschild, and he lived from 1873 to 1916. And so once Einstein published his theory in 1915, Schwarzschild, he worked it out. But unfortunately, he was in the military, he worked it out, but then he got an illness and he died, so he really didn't live to get credit for his work. But we give him credit, but he didn't live to, enjoy getting credit for his work. And so here you have I'm going to describe what happens as you come closer to the event horizon of a black hole. Now, the event horizon is the surface, and I got that in parentheses because it's not a surface, it's just a region of the black hole where once objects fall into it, nothing can escape back outward. And in order for something to escape outside the event horizon, it would have to be traveling greater than the speed of light. And then Einstein tells us that no matter can travel greater than the speed of light. And so as you come closer to the black hole, say from the accretion disk, you encounter the Earth. Okay, first it's a non-rotating black hole, so it doesn't have an ergosphere. So you encounter a photon orbit. That's where light is so strong that oh, I'm sorry, gravity is so strong that it bends light around in a circle, because light normally travels in a straight line.
I'm gonna commit suicide. I feel like Hitler.
So okay, so as you're traveling in, you encounter the photon orbit. That's the last orbit of any particle. Uh, and then as you go in, there's the event horizon. You encounter the event horizon. And once you're inside the event horizon, then you encounter what we call a circularity. I'm sorry, a singularity. And that's that dead star. But we don't know what happens to that star because we can't get out the event horizon. And also our physics or theory breaks down here general relativity, because the singularity has infinite, like very large gravity, infinite density, to where our physics break down and we would have to have a quantum theory for gravity, which we do not have at this time. Rotating black holes. Okay, rotating black holes allow us to extract energy. So the physics of a rotating black hole was worked out from Einstein's general relativity by Roy Kerr in 1963. And so here, say we're entering, we're inside the, we're coming from the accretion disk. So first we encounter, as we get closer, a stationary limit. Now notice that there's a budge here, and that's like the equatorial budge of the Earth. That's because of the rotation. So just imagine that we are cutting the this object in half. And so we encounter the stationary limit. Inside the stationary limit is the ergosphere. And inside here, if you go inside the stationary limit, you must rotate in the direction that the black hole is rotating. And so you can have particle orbits in here, and this is where we're going to extract energy from the by way of the Penrose mechanism. But here you have particle orbits. Now these particle orbits have been given a large amount of energy from the rotation of the black hole. And so we're going to find that you can extract energy outward from the event horizon. And the singularity here, it's a ring singularity because of the rotation. And it theory goes is that the ring is in the plane, in the equatorial plane. So everywhere outside of that is the force is repulsive, but if you get to the singularity, then it's attractive. Okay, what else? Okay, so this is the rotation axis and the event horizon. So before reaching, this is kind of to recap what I just said. Before reaching the event horizon, the infalling particle will enter into a region called the ergosphere, and it means energy sphere. That's where the term came from. So even though we always measure energy to be positive, the infalling particles inside the ergosphere can have either negative or positive energy. The negative energy particle can never leave the ergosphere, but the positive energy particle can leave. It can leave by Penrose collisional processes, which I will talk about, and escape from the strong gravitational pull of the rotating black hole. Right. Okay, so astrophysical quasars. Well, I had said, excuse me, I'm trying to kind of rush because I want to get to other things. Okay, I had said that black holes come in, different sizes. So quasars are the supermassive black holes, and then within a galaxy you have what we call microquasars, and they have the same properties as supermassive black holes, but their physics, the time scale of the way that they change is like very small. So for example, the jet for the quasar is at a steady state. And so we hardly ever see the jet, but we don't see the jet changing, much. But then for the microquasar, the jet can expand and decay over a period of a month. And for the microquasar, it's usually, it's associated with a binary star. And so this would be the microquasar, and it draws matter from this star, and then process takes place and the polar jets are emitted. The jet lengths are different. Quasars have jet lengths of the order of kiloparsecs. It's like 1,000 parsecs. And a microquasar has one for the jet is less than a parsec. Now, parsec, let me just say what, so that you'll have an idea of the jet length. A parsec is equal to 3.26 light years. And a light year is equal to about 6 trillion miles. Okay, and then their energies for the microquasars is larger because of the accretion disk. But if you take and do things in gravitational units, you'll see that at the same radius where you will have scattering processes for the microquasar, you have the same radius for a for a quasar. So microquasars are basically like scaled down quasars, and they're scaled down to stellar sizes. Now, this is a picture. This is like from when I first started working on quasars. And so this is the accretion disk, just to give you an idea of what the accretion disk is. Again, we're cutting the black hole in half. So this would be the accretion disk. This is a cooler accretion disk. The friction in this accretion disk heats up the iron corona like our sun has a corona. And this iron corona extends inside the ergosphere, and it populates those orbits in there. And then when smaller energy comes in particles, they can scatter off of those high energy particles and escape back outward. And when we say far away from the black hole, we usually say escape back out to infinity. And so here you have particles, the electron, positron pairs, and gamma rays. And so here at this time, we only knew that they were being emitted. We didn't know the structure of them before I worked out the Penrose. So this right here, don't worry about that. That's a little advanced. So over the years, what we started observing was that from observation, it appears that objects were formed in the accretion disk. Okay. Then as you get close, this would be sort of like the ergosphere. And then when the particles are ejected, they are ejected on these spiral-shaped orbits, or you call them vertical orbits. And this is what the Penrose mechanism would produce. Now, I'll talk about later, like this could equally be the magnetic field lines, but we'll talk about that. But let me just say how the Penrose mechanism could explain this, because the particles will escape in these vertical orbits, and because it's a plasma, then they will have a magnetic field along the z-axis. Go back. Oh, and this is the observation of it. And so this is from theory and what we believe, and this is an artist's conception. This is an artist's conception, so this would be the black hole, and it's dragging space-time around, and that's because of the mass. So remember I showed you the picture, the rubber sheet where the mass was warping the space-time or bending it. And so when it's rotating, then it drags space-time around, and then that's what you're seeing, and that's called frame dragging of space-time. Now this is another artist conception. So the question is, are these particle orbits, or are these lines from a magnetic field? The way that we measure that is something called the rotation measure, and it's proportionate to the electrons per unit volume times the magnetic field. So because it's a multiple of the two, it could be either the electrons dominating, or it could be the mass, the magnetic field dominating, or it could be both. So only observations and theory can tell us the difference. Now this is the the first picture of a black hole, and this is the black hole shot. And it was taken by the Event Horizon Telescope. And the observations were done in 2017 and published in 2019. So here you have, this is radiation coming from the photon orbit. And it's radiating because of synchrotron radiation. So we know that a magnetic field is associated with this observed object, or the black hole. And here are the polarization measurements. Now we're looking down the axis of the jet. So these, by the Penrose mechanism, these would be particle orbits, or they could be magnetic fields, or both. So since nothing can escape the black hole or the event horizon, the identification of a black hole is its gravitational influence on nearby matter. So that nearby matter would be inside the ergosphere. So the Penrose mechanism, again, proposed a way to extract particle energy from the ergosphere called the Penrose mechanism. So I'm going to briefly go through this. It's a simple derivation. So here you have a particle inside the ergosphere. Tidal forces breaks the particle up, or object. You know, at this time we were considering stars. So it breaks the star up into two fragments. So this is the initial particle. This is a trapped particle, and when it breaks up, this one requires a negative energy. Now remember, we are inside the ergosphere, and then the one that escapes has a positive energy. So that's E1, and that's E2 to trap, and E3. So from conservation of energy, you have E1 is equal to E2 plus E3. So if you solve for E3, you'll get that E3 is equal to E1 minus E2. But if E2 is less than 0, then E3 is going to have an energy of E1 plus the absolute value, you know, it's the two negatives multiplied. So it's going to be a positive. So you have E3 is equal to E1 plus E2. So that means that this particle escaped with the energy of this initial particle plus the energy of the trapped particle. And that's how rotational energy is extracted. So the extra energy comes from the rotation of the black hole, as it's giving particle energies inside the ergosphere. Now this is from Penrose paper. So you can see that he just simply, you know, explained this diagram like these are inhabitants up here, and somehow they send a particle in, or to a star. It increases in energy, and then they have other inhabitants, and they measure, it breaks up, and they measure the energy as one particle is falling into the ergosphere, and the other particle comes back out, and that's what they measure. So that's the classical Penrose process from his paper. The problems with the classical Penrose process is that if it's a star, then it has to break up with the fragments have to break up, be traveling greater than a half, 50% of the speed of light. Now we know that that's impossible. So that was one problem with it. And then so people say, okay, so we'll use particles, and particles can, elementary particles, they can break up at the speed of light. But then when you took and calculate the efficiencies, then the efficiencies were too low to explain, you know, active galactic nuclei or quasars. So to overcome these problems, I did relativistic scattering with inverse Compton scattering and pair production. And so it basically, from these processes, you can get high efficiency. So it overcame these problems. So this is a diagram of the results of me doing working off the Penrose process. So the Penrose, and I call it the Penrose-Williams mechanism, and that was because the people were working on the magnetohydrodynamic Penrose process, and they were running into problems. So that's why I, you know, called it the Penrose-Williams mechanism, because I wanted to distinguish it from those other mechanisms. that were having problems. So the Penrose-Williams mechanism for my dissertation, and then a 1995 paper and a 2004 paper. So it's a four-dimensional mathematical model which uses space-time frame dragging. And it appears to overcome the problems associated. And I say the Blanchard-Nye type model because that was the most, that was one of the popular models when I started studying quasars. And it's a popular model now, but it's still having problems, and I'll kind of go over those problems. So this model is a self-consistent model, and it constitutes a complete theory to extract energy from the black hole. And so here you have the accretion disk, which I showed you. Then the iron corona, which is have like a very high temperatures in the iron corona. So the iron corona extends down inside the ergosphere, and Penrose processes take place where, and I'll explain those in a little more detail, but when the particles escape, because of the frame dragging, they escape in these vortical-like orbits that's concentric to the polar axis or the D-axis. And then because it's a plasma, you have an intrinsic magnetic field being induced along the axis. So going back to this diagram, the Penrose mechanism, which was predicted before these observations, actually predicted what we would observe once our technology caught up with theory. The only thing I want you to look at on this diagram is that this is the curved black hole, the rotating black hole. These are important radii as you're getting closer to the event horizon. This is the ergosphere, and these radii inside here is where the Penrose process takes place. And so you have scattering at the marginal stable orbit, which is the inner edge of the accretion disk. And then you have these orbits. Now these are, so this is the stable accretion disk. These orbits are unstable. Then you have scattering at the marginal bound orbit, which would be Compton scattering inside this region. And then you have pair production of electron-positron pairs at the photon orbit. And so what this model gives rise to is that it can predict spectral ranges of particles intrinsic to black hole rotation by the Penrose mechanism. I need to take my hand off this mouse. I don't want to confuse people. So here you have, let me just kind of close my screen. So the overall results is that I was able to obtain the four momenta of particles escaping from the ergosphere. I was able to get the energy of a particle, its radial component outward, its theta component, and which is the polar component. Theta goes from the pole at 0 to 180 degrees below the pole. And then you have the azimuthal component, and that component is the component that's around the, say it goes around the equator from 0 to 360 degrees. So these are spherical coordinates. So what takes place is that before you have at the, for Compton scattering, you have an electron inside the ergosphere, a high energy electron. You have a low energy photon coming in from the ergosphere, from the accretion disk. And so they scatter. The electron is put on a negative energy orbit or a lower energy orbit, and the gamma ray or the photon escapes with the higher energy, and that's the wavelength, the frequency is higher. That's why I have it like the shorter wavelengths and then the longer wavelengths for the lower energy. Now at the photon orbit, which was the first time it was ever done, because prior to my derivations and analysis, we didn't think that particles could actually exist at the photon orbit in any kind of stable orbit. And they couldn't exist inside inside the equatorial plane. And before I did my work, we can only evaluate in the chronometric along the equatorial plane because we didn't have trajectories for particles that are escaping above and below the equatorial plane. So after I took and solved those equations for the trajectories, I was able to do scattering at the photon orbit. And so you have a photon, a high energy photon at the photon orbit. You have a low energy photon coming in. They pair produce. On the average, one of the electrons or electron pairs would fall into the black hole, and the other one would escape outward to infinity. And so that's how you got the pair production of electrons. Now, before that, like our observations showed that electrons were emerging from the cores because of the magnetic field and synchrotron radiation, but we had no idea how they were formed. And so also I found from my derivation that particles escape in the form of vortical jets. So all of these features, well, let me go, I didn't explain this. So these are the energies that you can get. So from Penrose Compton scattering up to 14 MeV you can get, and from Penrose pair production of electron-positron pairs, you could get energies up to 10 MeV for the thin disk, and when the iron corona forms, you can get up to 54 billion electron volts. And so now all of these items, 1, 2, and 3, are consistent with what we observed. Okay, I just wanted to put this in just to make sure that everybody understand what I mean by 3 dimensions and 4 dimensions. So here, this is, so say that this is your vector here. The radial component is in the radial direction. This is the theta component that's going from the z-axis down to negative z. And then you have the azimuthal component that's going around. And so that's what is meant by 4-dimensional space-time. You have 3 space momenta, and then you have the time component, which is the energy when you're considering momentum. I only brought this in just to show you that these are, this would be us globally. And so you have what we call a local non-rotating frame, where you take out the rotation and then you're able to apply special relativity without the interference of gravity. And this is for Penrose Compton scattering. So I had to obtain or derive these vectors and all of the angles, and I had to do it analytically, like, you know, using algebra, trigonometry, and geometry. And this is another one. You can see all the angles and everything that I had to derive. Now, this is another, this is like a little more detail of the vortical orbits. And so you have that are escaping from these radii, and they are in these vortical orbits. These are from Compton scattering, you get gamma rays and X-rays, and then from pair production, you get electron-positron pairs. So these would be in here, and that could be called what we call a spine, and this would be the sheath. So you have 2 distributions of energetic particles coming from the Penrose process. One more thing. So when these particles escape, they escape with these escape angles, and these escape angles are small for the energetic particles. And what it is, it looks like the particles are escaping in these coil-like distributions, and that collimates the jets. So I said strong collimation about the polar axis implies jets are relativistic particles. This is an artist's conception, but this is really close to what we're observing from the Penrose process, because the particles are escaping in these vertical orbits. And then once you're outside the effect of frame dragging, then the angular momentum transforms into linear momentum. And so here, if you have a magnetic field, you will have the magnetic field along the polar axis. because of the particles swirling. And then you have the right-hand rule. So with the particles swirling around, that would be like the current, and then you have the magnetic field along the pole. But once the frame dragging effect is no longer dominant, then the particles would escape in these linear orbits, and then you would have the magnetic field going around. And this is what we seem to observe. At first, you have particles escaping the magnetic field, particles escaping the vortic orbit, the magnetic field along the axis. And then once you're outside the frame dragging effect, then the particle motion can become linear, and the magnetic field becomes like a helix. Yeah, only thing I want, okay, so we always had a problem as to how these particles are being lifted from the lifted up into the jets, because gravity is attractive. So gravity draws everything towards the center, but then these particles were escaping outward. So it was a mystery, like how are they getting lifted out of the accretion disk or lifted into the jets? And when you study the curve metric, you encounter, or you study about this field, and it's called the gravitomagnetic field. It's the gravitational analog of a magnetic field, of electromagnetic field. It's not an electromagnetic field. This field is produced by the frame dragging. And so as particles are fall into the ergosphere, the frame dragging takes and create this gravitomagnetic field. It's sort of like a Coriolis field in a rotating frame. And this field, it resembles an electromagnetic field or a regular magnetic field. But the difference is that the magnetic field, electromagnetic field, or the magnetic field from the electromagnetic field, it has an effect on, it only affects charged particles. The gravitomagnetic field, it acts on all types of particles, irrespective of its charge. So therefore, it would have effect on massless particles or no charge particles, like photons. What else? So this would be so far away from the horizon, the gravitomagnetic field, it looks like the lines of force looks like a magnetic field from electromagnetic radiation or electromagnetism, but it's not. It's actually a form of gravity. So it's a gravitational field by Einstein's theory. And so here you have the inward gravitational produced by just the mass, that's gravitational acceleration. And then you have the gravitomagnetic field, which acts on particles that are moving. And that's why we say it's like a Coriolis force. And it resembles a Lorentz force, and I don't want to get into all of that. So here, just pay attention to this diagram. So this is the gravitomagnetic force and how it acts on a particle. And it's proportional to the azimuthal momentum of the particle, and that azimuthal momentum is what's extracted from the black hole due to rotation. So, and also the gravitomagnetic field is repulsive. So it's not like an attractive gravitational field, it's actually repulsive. And so here along the, so this is the polar angle. So this would be the equatorial plane. So in the radial direction, you have that force basically repulsive. So it's ejecting particles greatly along the equatorial plane. And then you have the theta component, which is the component that's responsible for particles being ejected into the jets. And you can see this is the equatorial plane. So this force is stronger in the polar direction. And so that's how particles are able to be emitted into the jet. And this is acceleration. So it accelerates the particles. I mean, ain't that a little bit. So these are just observations in how the Penrose calculation, how they are consistent with observation. And this is a quasar. That's a true observation, and this is from the model. And this is the accretion disk in true observations, or a true, how should I say it, a real model. So these are from observations. So you have accretion disk, and then you have particles here, particles being emitted here. Now this is power along this axis, and this is energy. And so with the Penrose process, I get this energy for Compton scattering from equatorial targets. This is for non-equatorial targets, and this is for electron-positron pair Penrose process. So you can see you get way more energy than being observed, but then like in this case, I let every particle scatters. So realistically, every particle is not going to scatter. So you can have the, you can fit it to observation. So the Penrose process is consistent with observation. And on this diagram, it's just showing the range of the Penrose Compton scattering particles are emitted, and this is the range of the Penrose pair production particles being emitted. This is for a microquasar. So this is observations, that's the accretion disk, and you have another emission of particles, and you have another mechanism of emission of particles. And this is what I calculated. So this would be the accretion disk. So I took one particle from the accretion disk and scattered, and had 2,000 scatterings. What I got back out was that I got a distribution here, which is consistent with this one. And then I got the pair production here, which is consistent with this. So I was able to match observations with my model. And these are, I'm almost done. These are plots of the radial component of the momentum. And so here I just highlighted, I put this in red, and I'm just going to use these two just to show you how energy is extracted. So this line right here, it represents the initial energy of the low energy photon coming in and scattering inside the ergosphere. And so these are after 2,000 scattering processes. I got all of these particles out, about 90% escape. All of this energy is from the scattering. This is what, so if you compare the energy of the initial infalling photon, then all of this energy is extracted, okay? And so now this is the energy. Now, if you combine the energy of the initial particle, the photon, and the target, then they would be here, okay, if you sum those. But all of this energy is what's being extracted from rotational energy of the black hole. And then this is for equatorial targets, like targets that were confined to the equatorial plane. And this is for non-equatorial target electrons. And so here you see the same, like this is the difference from the energy of the initial photon. All of this energy is being extracted. And that's from both of the particles, the target and the incident. So if you add up the incident particle and the target particle's energy, it would be here. And so this energy is spin energy or rotation energy extracted from the black hole. So I'm just gonna, these are just the, that's the theta component, and I'm not gonna, this is the same, from the same scattering process, this is different components. And so this is the theta component, or the polar component, and that's the azimuthal component, which is linear with the energy. So the larger the azimuthal component, the more energy you get out. And so remember that gravitomagnetic force in the polar direction is proportional to this. So the larger the energy you have, the greater the sturdiness of the jets as they are collimated and radiated along the polar axis. And this is a these are polar angles of the scattering particles, of the scattered particles, excuse me, the escaping particles. And so you can see that these angles are measured relative to the equatorial plane. And so the higher energy particles, they have a stronger polar-like distribution than the lower energy, but they are all escaping in these swirling vortical-like orbits along the polar axis. This is for Penrose pair production. And this is, this is not as clear cut. I can explain it in such few terms as I could the Compton scattering. But this is the radial component, and all of the radial components are positive because anything that falls in with the photon orbit, and this is where the scatterings are being done, then it would fall into the black hole. So you only have outward scattered escaping pairs. Okay, so those are the energies that you can produce from Penrose pair production at the photon orbit. And that's the polar component, and that's the equatorial plane. So you have jets. These are jets, and as the energy gets higher, the polar component of the particles get higher. And this is the azimuthal component. And again, that's the escaping angles. So if you look at this as a plane, it looks as though that the particles are being emitted toward the equatorial plane, but you have to actually look at it in 3 dimensions. I'm sorry, let me go back. In 3 dimensions to see that these are particles are escaping along coil-like distribution. And finally, when you calculate the velocity of particles in the azimuthal direction as they escape, these particles are escaping with speeds near the speed of light. So they are relativistic particles. So this is the speed of light, say at 1, and this is the gamma, which is tells us the energy of the particles. And you see that these particles, they quickly attain velocities comparable to the speed of light. So we were always like, it was a mystery as to how these particles being ejected in the jet with velocities equivalent comparable to the speed of light. And so the Penrose process can actually produce those relativistic particles. So almost done. How much time do I have? Everybody's muted. Okay, my stopwatch just kind of failed, so I'm just ad-libbing. So first, further results from the Penrose-Williams mechanism. The escaping high-energy electrons are expected to create a self-induced magnetic field, producing synchrotron radiation in the form of vertical swirling polar jets consisting with event horizon telescope observations. The escaping electrons could serve or act as low particles, allowing the Blanchard-Nye type model to work. Now, the Blanchard-Nye type model, in a nutshell, it says that the magnetic field of the accretion disk anchors to the black hole. And as the black hole is rotating, then energy can be extracted from the rotation of the black hole in the form of electromagnetic energy, not electromagnetic radiation, because with electromagnetic energy, you need particles, and the Blanchard-Nye model is having problems producing those particles in the magnetic field. And so the escaping electrons could act from Penrose process, could act as seed or loading particles, allowing the Blanchard-Nye model to operate. And at best, it can enhance the Penrose-Williams mechanism by further collimating and accelerating the particle plasma out to the observed distances of the jets. The Penrose mechanism does not need the Blanchard-Nye type model to extract energy from the black hole close to the event horizon where gravity dominates. And what we also, okay, where gravity dominates, let's just leave it right there. Frame dragging can produce symmetrical or that's even jets, or it can possibly produce uneven jets about the equatorial plane. And I found that out from calculating the gravitomagnetic field. Now, in my calculations of Penrose process, the gravitomagnetic field is already taken into account by the curve metric, but I calculated this field separately so that I can see what it was doing, how it was acting on the particles. And it's actually a component that would actually make the jets uneven. So you could have Doppler boosting in addition to frame dragging, possibly producing the uneven jets. But the curve metric, the way that it was derived, it will not allow for that to for us to see that because it assumed reflection symmetry above and below the equatorial plane. So if that's taken out and you derive a curve metric, then possibly we could see what the how uneven jets are being produced. That is the effect from the gravitomagnetic field. So, and next, no problems exist thus far with the Penrose-Williams mechanism, and it is consistent with the Event Horizon Telescope observations. So, does this rule out the Blanford-Zanaid process? Okay, or does the observation of the Event Horizon Telescope rule out the Penrose? The Blanford-Zanaid type process? So what we want to say here is that importantly, the Event Horizon Telescope observations measured a magnetic field from 1 to 30 Gauss, which is very small, very much smaller than that required for the Blanford-Zanaid model to work on its own, because it would require a magnetic field of about 10,000 Gauss to produce the needed electron-positron pairs to produce a synchrotron radiation with the magnetic field. So I just, showed this again. So this is the shadow of the magnetic field. These particles are coming from the photon orbit, which is consistent, the photon orbit, which is consistent with the Penrose process. And then these are polarization, saying that these are either particle orbits or magnetic fields. And the Penrose process strongly suggests that it's particle orbits. So importantly, and in summary, my theoretical analysis of the Penrose mechanism, it laid the groundwork for the advancements that we have made over the last 2 decades in understanding general relativistic astrophysical rotating curved black holes. And my contribution consists of creating the first mathematical model calculation that is successfully extract particle energy momentum from the ergosphere of a rotating black hole by Penrose inverse Compton scattering and Penrose pair production at the photon orbit. So this proved that the Penrose mechanism works. Secondly, we were able to create, I created the first 4-dimensional Monte Carlo. Monte Carlo means a sampling of numbers on the computer to sample the way that particles are emitted, the angular distribution of particles. And so I created the first 4-dimensional Monte Carlo computer simulation of the model to show that high energy particles escape in the form of bipolar vertical swirling jets, consistent with observations of quasars and other active galactic nuclei. And here again, here's a picture, featuring this polar jet, artist conception polar jet. Now, you don't have to worry about these, but it's like I derived the equations for the conserved energy and angular momentum for non-equatorially confined circular trajectories or orbits about the curved black hole. Remember, I said they only had orbits that were confined to the equatorial plane. So this allowed us to calculate orbits that are outside the equatorial plane, and thus I was able to get jets out of it when I considered those particles above and below the equatorial plane or non-equatorially confined orbits. So most importantly, these derived conserved energy and angular momentum, were the first to solve the equation of motion for particles being accreted onto the black hole. And so from that, we were able to, they were able to create general relativistic MHD calculations because my model provided the blueprint for these simulations. These simulations evolved to my steady state solution, which is what we observe when we look at quasars. They are in a steady state, basically. And it confirmed my model calculations and are now, these simulations are now being used to confirm general relativity with event horizon telescopes and to predict properties that should be observed. And finally, my conclusion. Okay, we now have evidence that black holes exist in nature. Black holes that exist in nature are most likely rotating. Supermassive black holes are indeed fascinating objects in the universe and might be the heart of galaxy formation. And it appears that the energy momentum is being extracted by Williams, my analysis of the Penrose mechanism, and perhaps enhanced by the Blanford-Deniot type model at best. And finally, I will conclude there. And I do want to say to students that are inspiring to be scientists or whatever you're doing in life or whatever you choose to do in life, it's like find something that you're passionate about, that you love, and just work at it. And no matter what difficulties or challenges you may encounter, just know that if you just keep on working at it and believe it and work hard at it, that one day you'll be there, and have faith in God. And that's it. And thank you very much.
Thank you so much, Dr. Williams.
Yeah, how my stopwatch stopped. So what was my time?
You're probably an hour and 20 minutes, but we got them here till 5 o'clock. Doesn't matter to me.
Oh,
so
good.
You can keep going. You can talk as much as you want. You know, the one thing I think you really wrapped up at the end, because most of us were very unfamiliar with a lot of the things you're speaking about, but you have so much passion and you have so much energy. And I think that's what I want my students to take away from this. I mean, think about what this woman has accomplished, what this doctor has accomplished. I mean, we can't even wrap our heads around this. I'm trying to come up with questions here to you know, give you something to think about. And I have a question that I do want to bring up, but I want to hear from you guys. Like this is impressive. You know, we learn about Einstein, we learn about Isaac Newton. They were alive, Newton hundreds of years ago and Einstein 100 years ago. This is a real life, you know, physicist here. This is impressive stuff. At the very least, you're welcome. But at the very least, you have to recognize the fact, as she pointed out, whatever it is that's going to get you to be that excited as she is about black holes, you got to find that. Maybe it's within the sciences, maybe it's not. But that's why you're here, to find that.